Before we move on, I think it's always better if you can have a better physical feeling of the things that you are learning. So here is very interesting Phet Simulation. You can download, so you simply just have to click and then you just download it, and then you will find all these things. Okay, and what you could do is once you started it, you could have well, there is a charge, and what you can do is maybe you can put a positive charge and see what happens. And apparently they will repel each other because they are both positive. So in order to get this attracted towards these, this is like the gold gate, and you just have to go inside like this. Okay, and this is a practice. So what you can do as well is you can try to look at the arrow. Actually the arrow is very nice. You can take it away. I think you could you? Okay, by the way, this is field also, you can activate it. And also, yeah, you can change the mask if you want, but then that's just change the acceleration only. Okay, so you can see this is how it will happen. And apparently the most important thing you see is that when, say now my positive charge getting very close to this black positive charge, the force by the length you can tell increased significantly, because again the formula tells you that is inversely proportional to the separation square. So that's why it's not linear, but then it go much faster. Okay, and when it is further apart, it will become much less in that case. Okay, so maybe something that you can try to play around with it and see whether you can get a better feeling towards it. Okay, so I'll put the link in the description. Okay, so let's move on in our task book on page 200. Okay, so we talk about electric field right now. Once again, you can recall the gravitational field, and if you recall gravitational field, the way that we calculate gravitational field is more fundamentally is F is, well, you should say G equals to F over M. That means how much force you experience per unit of mass, per kg on the object, and that is called the gravitational field. And then from that they can experience a gravitational force. Okay, so G is the field. Similarly, for electrical field or electric field simply, we have something similar. So the symbol is E equals to F over Q. So if you're saying gravitational field is acting on the mass, then electric field is depending if you are having charge. Okay, so again, very symmetrical. When you look at this, I will really hope you can try to pay attention to the details. So once again, the keywords. So for example, like force per unit charge, which is explained by the equation. Another key point is small positive charge Q, which you find small point charge or small point mass is very similar to gravitational field. But there's one more new thing that is called the positive. Okay, positive here, which of course you don't find it in gravitation because gravitational field is always attractive. So what we have here is, because when we talk about the field line, we are always referring from positive, as we always say, from positive to negative for electrical field. I don't know why we are defining like this direction. Someone defined it, but we have to follow the tradition apparently to be systematic for communication. So that's why when you, for example, imagine this picture on here, so you find, let's say I draw another positive charge here, then you will find these positive charges will experience a force that is repelled by these positive to the left, right? So then apparently you can see the direction of the field line, which is at the back here. This red arrow is pointing at the same direction as the force also, okay, no matter where it is. If you somehow think of a negative charge instead, for example right here at the bottom of this positive charge, what this negative charge will experience is actually an upward force. So apparently this direction is opposite of the field line. So that's why in the definition we have to mention the word positive, because it's only experienced by the positive charge, the direction is correct, while for negative charge the direction is opposite. So that's why you have to specify the nature of the charge here. Think about another situation. All right, let's double check it. If you have a positive charge here, then that positive charge would be attracted towards a negative charge here, which is the same direction as the field line, the background, red lines from the background. So this is still consistent and working very well. However, if you try to put a negative charge, let's say here, then this negative charge will experience a force that is pushing this negative charge to the right. Again, it's opposite to the field line. So that's why we have to use again in the definition saying it's a positive small point charge. As for the unit, you can guess. For F, it is Newton. For charge, it is Coulomb. So that's why the unit for electric field strength, E, is Newton per Coulomb. Okay? Similar to what you did in the quiz in chapter 6, we had a question about saying F equals to G m1 m2 over r square, and then you also have F over m equal to gravitational field strength. And then if you combine these two equations together, you can get the equation of G, which is the same thing. Let me just write together, equals to G m1 m2 over r squared divided by the m, which could be m2. You cancel it out, you get G m1 over r squared. Similarly, you may have the Coulomb's law, which we covered in the previous video, together with the new equation we learned about the electric field strength together. You substitute this F into this F, and then you can get the new equation. Okay, you cancel the small q out, and then you get getting this equation. Okay, and this equation is something that you can you find it? Oh, actually you cannot find it, but you can actually find it, I'm sure, in chapter 10. Okay, I know chapter 10 is in HL, but then you can still learn where you can get the resources. So basically it's right here. Okay, so where you can derive it by yourself. So not exactly the same equation. Okay, so let's take a look below. So after that is talking about current. For this one, I would like you to pause the video and take a look of the textbook. If you can try to read the page and also this page. Okay, and one objective I want you to do on the note is I ask you to derive the equation of current equal to NAVQ over here, which is apparently here. And this is a very important equation where you have been provided in the data booklet also right here. But I think if you try to prove it by yourself, that really help you to understand the meaning behind, especially the meaning of each variable, like what N, A, V, and Q represent. Okay, so pause the video and try to read it and try to prove it yourself. Okay, so right here I've done the proof already, which let me show you. So what you have to do is first of all, we have to, when we try to derive something in physics, we always have to start with the definition. As I always emphasize, there are so many equations. If you look at the data booklet, there are so many equations. You have to really realize what are being defined and what are being derived. So for example, if we look at let's say this one, alright, chapter 2, work, energy and power. The first one, this one is about work done, and this is being defined. There's nothing we can argue about it. For KE, for elastic potential energy, for gravitational potential energy, these are all derived from the definition of work done. So this is a difference. And therefore, when we are working with some new equation, we have to start with the very basic thing, which is a definition, which again you cannot argue. For current, the definition is how much charge change, delta Q, charge change per unit of time, delta T. Okay, so what you can consider is you can try to consider a circular wire like this one, and then imagine inside there are some electrons. So these are electrons flowing inside with something called a certain speed. The speed is called drift velocity. Okay, just take it as velocity first, but I'll try to explain what drift velocity actually means. Nothing to do with the car drifting. Okay, nothing to do with that. If you try to look at this diagram, then you find out if there is a time t second, let's say 1 second, 2 seconds, 3 seconds, doesn't really matter. The distance that moved by the electron to cover a certain volume is calculated by v times t, because this is the distance that it traveled through the wire. Okay, so this is the distance that it traveled. At the same time, since you see that there is a variable called n in the equation, if you try to look at definition, n is a little bit like density. It's saying that how many charge carrier per unit volume. So like I said, again, similar to density. You may want to write it down somewhere on your notes or your textbook. The idea is very similar to density. Be careful with my wording that I said here is charge carrier, but not just charge. So what it means is electron itself is a charge carrier. Okay, not the charge itself. We should know that. I mean, you should know that from chemistry. Electron has a charge of -1. So -1 is the charge of electron. Again, electron is a charge carrier, carrying one negative charge. Okay, so the most important thing is if you want to calculate the number of charge, actually I missed a word, charge carrier, then we can calculate simply, since again n is number of charge carrier per unit volume. So what we have to do is times the volume, then we can find how many carriers are there. So basically how many numbers of electrons are inside. So n, which is like the density, times A, which is the base area, times Vt, I should say. Okay, I missed out the T here. Vt, which is the distance of this. So basically it's the same as when you do maps to calculate the volume of a cylinder. Base area times the height. So A times V times T is a volume, and then times n, then you can get the number of charge. At the end, what you can get is what you have to do is to refer back to the fundamental definition back here, because what we want to know is not just a charge carrier, but also how much charge. So basically you then have to times it with Q. So N A V T times Q is actually the total charge over this wire over a period of time, delta T. So delta T is the I. Okay, so in that case, I should actually put delta here as well, delta. And then in that case, the T, delta T would cancel out. And this is how you get the final equation, N, A, V, and Q. So N, A, V, and Q like this. Okay, notice that the Q, charge of carrier, is basically the one you have in the data booklet, which is you can get from the first few page here. Again, elementary charge 1.60 times 10 to the negative 19, that one. Okay, so if you're okay with that, then I would want you to pause the video and try to do these two questions. Okay, pause the video and try to do these two questions now. Okay, let's talk about the answer. So for 5.5, they said there is something provided in the question. So here's the I, here is the R. Be careful, this is mm. And then they want you to, oh yeah, they provide you the N as well. You can also see the unit, which is, like I said, how many per unit volume. So this is volume. And the hint is you have to be careful with the Q in the equation. So once again, the equation, you should state it first. I equals to NAV times Q. I is 1, which you get it already. N, you just substitute. And then for Q, is actually from the data booklet, once again, the elementary charge, 1.6 times 10 to negative 19. The tricky stuff, however, is probably the area, because be careful, this is radius. So assuming it is a circular wire, we always assume it's a circular wire, and then you have a radius of 2 mm, then you have to recall the area is pi r square, okay, equal to the area. So this is how you can get the answer here. And be careful, again, all this has to be in SI units, so mm convert to meter, divide 1000, and you can get the answer of 5 times 10 to the negative 5 meter per second, which is 0.05 millisecond. I think from the textbook, if you try to look at the answer, I think they did this part correctly, but then when they convert to this, it is wrong. Okay, so be careful with that. It's even slower, and it's surprisingly slow. If you think about the speed of the electron moving in the wire, then you probably cannot accept that. And that's the same when I learned it in secondary school, that I don't feel that, hey, how can it be flowing so slow? And there is a question that you may think about, is that since the drift velocity of the electron is so slow, so how come the light can switch on immediately without delay every time you use the lamp? For example, now if you go to switch off or switch on your light, it will go on or off immediately. So how come is that? Okay, if you want to think about it, pause the video now and think about that. So the answer is actually because the electron itself is fully packed in the wire. So imagine you got let's say just simply battery with the lamp. I hope you still remember the symbol. This is a lamp symbol. Okay, right here. So what happened is the electron are everywhere along the wire. So once you apply or switch on, like connected the switch, then it creates a potential, positive to negative. Actually, I should do the opposite direction, because the electron actually flow in this direction because of negative repelling electron. So since the negative repel this one, and then this one will continue to repel the next one and next one and next one and next one and next one instantaneously, and so the light will be switched on simply. So this is the reason why when you switch on the light, it doesn't take time for it to travel for such a long way and long time, and it will be switched on immediately. For the next example, let's go back to our notes here. Alright, is one of my favorite question because it's quite counterintuitive and quite interesting to apply the equation qualitatively. So once again, apparently you have to use the equation I, let me just copy again, I equal to NAV times Q. And what it said is now this cross-sectional area A, let's say, and AB are different, so it will become higher. So what you can do, like how we usually analyzed the physics problem, is by drawing arrows. So A increase, and then think about what what happened to the other 4 of them? First of all, I think everyone should know that n remain the same because n actually depends on the material. Some material will have more mobile electrons. If you remember, we talked about in the previous video about conductor and insulator. This is something to do with the conductivity of the material itself. So for example, metal will have more, while plastic will have very, very little. Similarly, since we always talk about the electron drift velocity, so then this also remain the same. So let's put a cross here. At the end, what matters the most is, would the currents or would the velocity be changing, or do they change at the same time, or do they remain constant, or what? The answer is that currents will remain the same, while in that case the only choice that V has to compromise is to decrease in this way. Okay, so here I ask you a question, bonus question here. What happened to the water tube in the lab? If you remember those tube in the lab, in IS lab or chemistry lab, I am 100% sure at a certain time when you study in secondary school, or at least you have witnessed it, some people, what they do is they would try to open the water tap and they would squeeze the head of the tube. So let's say this is a tube, and then they would squeeze it, and then what happens is the water will flow much faster. I hope you can imagine that. And so basically this is what happened, but opposite. If you have the area decrease, then velocity will increase. So basically that explains what happened when people try to play around with the plastic tube in the lab. And so back to the question, so how come, or how do we actually know that current remain the same then? At least that's the question I would ask when I was a student. I think the most important thing that you have to understand and accept that is, again, current is delta Q over delta T, and that's something to do with the flow rate. Imagine the water pipe. Let's say it flow 1 kg per second. That's a lot, of course. 1 kg per second. No matter what happened to the water pipe, no matter it's large or small, etc., that will be the same amount of water that flowing through. So let me draw maybe more visually. Let's say this is the amount of water that get flow through, okay, in 1 second, and then for B that would be probably the same. Well, it should be exactly the same volume, but apparently it will be much less in that case. So the amount of water would be the same, while the velocity accommodate to be faster or slower, so that to keep the flow rate the same. Because simply, if you recall one thing, water is incompressible. You learn in year 9. Alright, you cannot compress them, unlike air. Air can be compressed, but water you can't compress them. So when this water comes in here, they will push the later water away for sure. So the current must stay the same in that case. And that is a very important concept.